everyone, I'm Charitsis and I'm a PhD candidate at Stanford University. I would like to give you a short presentation of our work on quantifying decomposition in CS1 programs. First, I would like to touch upon the motivation behind our research. One of the fundamental human processes in software development is problem solving. It is a cognitive process of the brain that searches or infers a solution for a given problem in the form of paths to reach expected goals. Researchers in computer science education have long been interested in the relationship between problem-solving skills and programming abilities. The strategies that novices adopt while solving a problem affect their performance. The two most recognized design paradigms are top-down and bottom-up programming. The top-down development starts by implementing the most general modules and works towards those that provide specific functionality. The bottom-up development first implements the modules that provide specific functionality and then integrates them into more general modules. In practice, there's no pure bottom-up or pure top-down design, but a mixture, even in CS1 where the programs are simple. A problem solver attempts several approaches on the path to the final solution. Problem decomposition is not binary. As a higher layer cognitive process, it interacts with many other cognitive processes such as abstraction, decision-making, inference, analysis, and synthesis. It manifests to a different extent among individuals. Splitting the main task into subtasks in a program can differ between individuals. Not all students decompose the problem in the same way and to the same extent. Similarly, there's a spectrum for the time that decomposition In some solutions, it becomes apparent early on, while it is not evident until later in others. It would be immensely beneficial if we could find where a student's solution lies in the spectrum and compare it with the solutions of other learners. That became the motivation behind our research, which tries to answer two questions. First, how can we quantify the student's ability to break a problem into simpler tasks from the source code? And second, how does this metric relate to the time it takes to deliver the solution, its complexity, and the student's performance? To quantify decomposition, we can consider the two extreme approaches, the top-down and the bottom-up, although in reality they rarely exist in purity. We draw conclusions in each case and use them to develop a metric that captures how broad the student's view of the problem is. Let's say, for example, that the challenge is to write a program that plays tic-tac-toe. In a top-down approach, students use tab functions to draft an initial solution and then add the implementation for each function. In a bottom-up approach, students implement tasks with specific functionality first and then integrate those functions into the final solution. The end product, which may be the same in both cases, does not reveal the software development path. Let's compare the two approaches side by side. Let's focus on the function names and specifically the nouns in those names. Why nouns? In object-oriented programming, entities are often referred to as nouns and actions that determine their behavior as verbs. Function names systematically couple these verbs to the entity associated with the action. Let's count them in every step. In the first step, there are 4 distinct nouns for the top-down and only one for the bottom-up approach. We do the same for the remaining steps. The example made a few simplifications to highlight the basic concept of our method. As mentioned, novice programmers do not develop their programs using either a top-down or a bottom-up approach, but a combination of both. Moreover, not all functions use nouns. Finally, they do not always reflect on key problem tasks. For example, helper functions can also refer to nouns unrelated to the problem and must be ignored. We will address these simplifications later. We built a system around the concept that we just covered to quantify program decomposition from the source code and analyze its impact on program complexity and student performance. Let's look at it. To collect the data, we modified the integrated development environment tool that students use to code so that it creates a repository on the local machine and commits a snapshot to it every time the program is saved. Note that the program is automatically saved when students modify it and then try to run it, or when they manually save their work. Nevertheless, the data collection in stage 1 is independent of the approach as long as we end up with a set of program snapshots accompanied by timestamps. Next, a parser processes every snapshot retrieved from the local repository. The role of the parser is dual. A. It creates a list with the function names in the program, and B. It captures metrics related to the program's complexity to evaluate decomposition. Specifically, we used McCabe's cyclomatic complexity metric and tracked the software lines of code. Counting the number of lines can be challenging because of the differences in the code style among programmers. For example, person A writes a piece of code. Person B writes the same piece of code but uses a different style. So how many lines of code is the first program and how many is the second? Shouldn't both programs have the same lines since the code is identical? Our parser constructs an abstract syntax tree from the program to address this issue. ASTs separate how the code is represented from how the code is written. Thus, the internal representation is the same in this example. Nevertheless, we cannot count the number of lines directly from ASTs. First, we apply standard stylistic formatting conventions to every AST, a process known as pretty printing, and then capture the software lines of code from the output program. Next, we try to detect the main entities of the problem from the function names. Here's an example that shows how we do this. We process the final snapshots for all students and extract the function names. We then tokenize them, which means that we split them into component words. The tokenization rules are subject to the naming conventions of the chosen programming language, such as camel case, snake case, etc. We then detect the nouns. We singularize them since both plural and singular forms refer to the same entity. Finally, we aggregate the nouns from every student and create a histogram with their total frequencies. The most popular nouns account for the main entities. Detecting the nouns is not as easy as it sounds. One may be wondering why, since part-of-speech taggers are more than 95% accurate. However, most of them are trained from tree banks in the newswire domain, such as the Wall Street Journal articles. In other words, they are trained from a grammatically structured corpus. In our situation, we have function names with no grammatical structure, which makes tagging quite challenging. We created an unsupervised model that takes advantage of domain-specific characteristics and has satisfactory accuracy. The model identifies the nouns and function names with 62.6% accuracy. Although this is much lower than the part-of-speech tagger performance on full-text articles, it meets our needs to identify the most frequently said nouns among students. Once the main entities are identified, we analyze every student snapshot. We go through the same steps as for the final snapshot. We detect the nouns in the function names of the given snapshot and count how many of them are among the most popular nouns. In other words, we count the main entities. Given that the timestamps for the collected snapshots are available, we can plot the number of entities over time. In this case, the plot looks like this. The specific snapshot that we used in this example is right here. To quantify the student's ability to introduce early the main entities found in their final submission, we define the entity progress ratio APR as the ratio of main entities in the last snapshot over the main entities in the first snapshot. Using linear regression fitted values, the mathematical expression for APR becomes this one. From the formula, we calculate the APR for the particular student. We do the same for another student. Although no one used a top-down or a bottom-up approach, APR allows us to compare them. Student A has a broader view of the problem than student B, who focuses on a single subtask at a time. We just described the fourth stage of our system, the classifier that calculates the APR for every student. We classify the students into two groups, those with low APR with value at least half a standard deviation below the median, and those with high APR with value at least half a standard deviation above the median. The APR measurements are used in the fifth and last stage to compare submissions. Each solution is evaluated on 3 criteria. First, the time to develop it. Second, its complexity. And third, the student's grades. We process the timestamps to find the net time that the learner worked on the problem. To capture the problem complexity, we used McCabe's cyclomatic complexity and the software lines of code as mentioned earlier. For the student grades, we considered both the assignment grades and the exam scores. Let's look at our findings. We analyzed the submissions for 2 assignments by 250 students, a total of 78,500 code snapshots written in the Java programming language. One assignment is before the midterm exam and the other is before the final exam. The assignments are structured such that the deliverable tasks are well defined. The students are given explicit directions to clarify the expected functionality and ensure that the problem is well understood. Also, the description order probably aids the inexperienced student that is often unsure of how to begin. Nevertheless, the program decomposition is left to the student. The analysis suggests that program decomposition reduces substantially the time it takes. In both programming assignments, the students with low EPR finished much sooner than the other group. The difference in time between low EPR and high EPR is statistically significant, whereas the effect size is moderate. Though cyclomatic complexity and software lines of code are not strictly measures of decomposition quality, high complexity correlates with opportunities for further decomposition. We notice a higher correlation of student development paths with exam scores than assignment grades. Researchers who made a similar observation believe that the development path provides rich information regarding students' understanding of concepts beyond their final product. Our investigation backs up their explanation and also reveals a second reason. A weekly programming assignment imposes substantially more relaxed time constraints than a 3-hour exam. As mentioned, decomposition helps solve a problem faster and therefore increases time efficiency, leading to higher exam scores. Before concluding our presentation, we would like to go over a number of precautions to preserve the generality of our method. Our method relies on source code rather than other more subjective approaches such as surveys, think aloud experiments, etc. We used an unsupervised learning model to detect the main entities without prior knowledge of the programming assignment specifics. The source code parser does not depend on the programmer's formatting style. The APR is normalized to allow comparison between students. Despite our efforts, there are still threats to the reliability of our work. First, we observed frequently that the first snapshot contains only the main function. Therefore, even if the next includes a complete list of stub functions, the APR value will be deceptively high. We found that in most cases, skipping the first 5% of the snapshots compensates for the early, transient development stage. Nonetheless, the 5% choice is arbitrary. Similarly, for the threshold for the main entities. A noun must have a popularity at least one standard deviation above the median popularity to be considered a main entity. Moreover, we found that students with high EPR perform slightly better in the programming assignments than those with low EPR. However, it remains unclear if the difference is statistically significant. In the first program, the p-score is barely below 0.05 and the second is 0.077. A greater concern is the effect size. The effect size is moderate for the problem-solving time, the cyclomatic complexity and the exam score, and low for the lines of code and the homework assignment score. Finally, although the sample size of 250 students was sufficient to derive statistically significant results, a larger dataset in terms of the sample size and the number of assignments can be helpful for validation. And that concludes our presentation. Thank you so much for your attention.
Thank you very much, Charis. Question time.
Hello, Mong from CMEU, and I want to ask: can we just count the first period of time, how many functions they have created to see whether they may use the top-down or bottom-up approach? Because if they use top-down, they may create a lot of function calls, And if they use bottom up, maybe they work more on the first function. Yeah.
Yeah, the answer for that is the following. Generally speaking, that might work, but I can think of a thread to that, approach by having helper functions. Like for instance, if you have someone who's using a very long function to implement a task, and then you have another person that is just taking the very same thing and using many helper functions without actually splitting the main task itself, but just having, let's say, a very thin, like for instance, if you want to calculate the average, and then you say, okay, I'm going to calculate first the total sum, and then I'm going to calculate the denominator, and then I'm going to, so that's, in that case, it's probably not going to work because it does have to do with the main structure. It's mostly like helper functions within a very long function that could cause a problem in that case. And that is one thing. And then the second thing is, when it comes to time, then what if it takes more time for a student to come up with the same solution that it's faster for another student? That would also not really work. So it has to be something that allows you to compare different solutions in a sense. And I think time is not very reliable in that sense, given that students complete in different times. So you have to sort of normalize the approach. Like if it takes me, for instance, an hour to finish my work, and then you have another student that takes 3 hours, then you have to somehow normalize that.
Additional questions?
I agree with you. We cannot set sorry, it's a follow-up question. So I agree with you that we cannot set a threshold in terms of the time. But still, can we just count the function calls, the number of function calls instead of the detailed nouns of those entities? Yeah, what's the particular thing we need to consider? I guess there might be some reasons. Yeah.
The reason for that is the following. The reason is basically you have to consider which are the main tasks. Like for instance, you may have like functions that are doing side things. Like, it doesn't really like for instance, if I have a function that is set, let me give you a concrete example. Let's say I have a function that calculates the average given an array of integers. And that I'm using that functions in 4 different places. Okay, now imagine that I start by writing this function first, and then I'm writing 4 other functions that are calling that. So now imagine that I'm doing sort of the opposite. Like I'm writing one function first that calls this one, and then I'm writing a second function, and then I copy paste the code for the first one that calculates the average. So I end up with double the number of functions by just repeating the same helper function. So in that case, it's misleading because I'm not really decomposing this thing better than before. Like the problem there is that you want to filter out the helper function and focus on the main tasks. Let me put it in simple words. Like when you decompose the problem, you're gonna break down a main task or subtask to simpler tasks or subtasks. And helper functions are not really doing that for many reasons. A, because they can be shared across multiple tasks, and B, they may be relevant to the thing that you want to use. Like another example is like libraries, like functions that you see in libraries, which are already provided there. So I don't know exactly your background so that I can be more technical, or if I cover that, or if it's not clear, I'm happy to answer another follow-up question.
Yeah, thank you very much. Yeah, and actually I like your idea very much to analyze through using this method to analyze their strategy on solving the programs. Thank you.
Oh, thanks.
Questions? I have one question, Charis.
Sure.
There is one on the web. Maybe.
Sorry, can you repeat that? You're breaking up.
Okay, I will make my question first. What do you think is the causal relationship between low APR and the grades? Why students with low APR perform better, or you think perform better in the exams?
That's a great question. So I think I partially covered that, but I can explain that in more detail. So one of the findings is that if you decompose the program better, you're finding the solution faster. Like that was one of our findings. Now, if you're given a homework assignment, let's say you have to turn your homework, turn it in a week from now. So there's plenty of time to do that, even if it takes you 3 hours and you're bad at decomposition and you finish a task that takes 3 hours, like a task that should normally take 1 hour, you finish it in 3 hours, you still have plenty of time. So there's no real time pressure there. Now, let's say that you have two students, one that has developed, decomposition skills, and another that is struggling with decomposition. And now you're given, let's say, a 3-hour exam. Now there's time pressure. Let's say you have to solve 5 problems within 3 hours. There's no, let's say, luxury that, okay, I'm gonna do it slowly, and then if I'm not good at decomposition, the time is running. So that time pressure is more important. Given the time pressure, it's more important that you have developed a skill set that allows you to derive faster to the final solution. And decomposition is one of those skills. That's why we believe that we saw that big difference in the midterm exams, and it wasn't that much of a difference in the homework assignment grades.
Okay, thank you, Charis.
Yeah.
Another question? Okay.
So I think I can understand the result that for people who can come up with the overall idea, the planning how to solve the problem, and from the top-down approach, they kind of know how to solve the problem. While for students who working on a particular local function, maybe they don't do planning and don't know how to solve the problems from the overall view. So I think the result for me is somehow reasonable and predictable. And I'm wondering, because you also have the time-wise snapshots of the codes, so how can we further utilize the results to do some like prediction or like intervention in case, based on the time-wise, we know that, you need to kind of have some top-down idea, do some planning instead of working on a particular thing. Yeah.
That's a great question. That's something we have considered. That's an excellent question, actually. And what we have thought is mainly sort of intervention. Like, if we see down the road, like in real time, that EPR is high, it means that you're not really great at decomposition. So at that point, we may have since we have sort of hacked the ID that students use, perhaps there could be a top pop-up menu that says, think about simplifying your, give the students some hints or instructions or some warnings that perhaps your code gets too complicated, or try to break it down to simpler tasks. And as long as we detect that EPR exceeds a given threshold, so that the student at least has that in mind or gets a warning or something like that. That could be a start, for instance. Then it also depends on how much help you want to give the students. Like you don't want to give them the answer, you just want to warn them so that they can think at least about it. So that would be a first approach. But for sure, there's many more ideas than that. But it's mostly on the intervention side rather than predicting.
Okay, questions? Not. Thank you, Charis. Thank you for your both
Thank you
your
so much.
presentations.
Thank you.